Well, hello everybody, and welcome to our final edition of the Weather Unit with Physics of the Universe. And if you are watching this in the 2020 year, this is the final video of the year. You guys are almost done. The last thing I want to head over is this is part B of what we were talking about last time. We already started talking about cloud formation and air masses. But this is getting a little bit more involved into how do clouds actually form and how does this control the weather, particularly here in the United States overall. So let's get on with it. The first thing I want to start off is a little bit of review from our previous lessons because we're kind of gathering some ideas from what we've talked about earlier. First, remind you that warm air, when you get air warm, it becomes less dense than cooler air. So if it's less dense, that means just like if you threw a piece of styrofoam, which is less dense than water, it would float on top of the water, right? Well, water does the same, or air does the same thing. The heat expands the air, and as that air expands, it becomes less dense and it starts to go up. As a result, also cooler contracts, becomes more dense, and it sinks down. So think of it as warm air is rising. If you're standing in an area that the air is rising, then you're going to feel less air pressure than usual. So we call that low pressure. Cooling air is sinking air, so the air is sinking on you. That means you're under more pressure than usual. That would be high pressure. The number one, we talked about different ways in which we heat up the atmosphere. The number one way that we heat up the atmosphere is by the atmosphere touching the surface of the earth. Really, most of the energy that we get in our atmosphere is caused from the sun heating the surface of the earth up. And when it heats the surface of the earth up, it touches the air. So the air right on top of the earth is what's getting heated up. So you heat that air up by heating the surface up. And then that air starts to rise. Now, the further that, as that air goes up and up and up and up and up, the further that air goes up, the cooler it starts to get because it's getting away from the surface of the earth. So we have that's called the environmental lapse rate, or sometimes referred to as the adiabatic lapse rate. And in this case, when we talk about what's called the dry adiabatic lapse rate, that means that there's no moisture in the air. The air is not saturated with water. For about every 100 meters, the temperature drops by about half a degree Celsius. So keep that in mind. We're going to come back and talk about that in a couple minutes. Moisture, water vapor, is also called humidity. Relative humidity is a measure of how much actual moisture there is in the air divided by how much moisture that the air can hold. So this was in our last video, and you can see the little glass here on the side. What happens with a glass of ice water? Why does it get all wet on the sides? It's not the water leaking through. There's moisture in the air, and if the moisture is in the air, what's going to happen is right now it's in vapor form. Right now there's moisture in the air in the room that I'm in right now, and what happens is that the room at this temperature can hold that moisture. However, if we drop that temperature, then the air can't, the colder temperatures don't have enough energy to hold the moisture in the air. So what's happening with this glass right here is that the air around the glass is colder than the air in the rest of the room. And any kind of moisture that's in the room is going to reach that point to where the air can't hold it anymore, and it's going to condense. It's going to turn from gas state to a liquid state, and that's what's going on with the condensation on this side of that glass. And that's going to be a very important part of what we're going to be talking about today as well. So when relative humidity reaches 100% in the air, it can no longer hold it as water vapor. It must condensate, turn into liquid, turning that water vapor into liquid water. So this is a magic point. We talked about this in the last video. This magic point in which we reach 100% relative humidity or saturation is called dew point. Okay, so that's enough review. Move ahead a little bit. Let's talk about clouds. Clouds up in the sky, how do they form? Oops, went the wrong way. How do they form, so forth and so on. Basically, what you're looking at is in a cloud is that there are basically three things that have to happen. Number one, you have to have moisture in the air. You can't make a cloud unless there's water vapor in the air first, period. All right, so if you're out in the middle of the desert and you're not seeing clouds, it just means that there's no water vapor in the air. You may have rising air, but it doesn't have any water vapor in it. So that's the first thing. The second thing that you need, and I kind of get ahead of myself here, so you need to have humidity in the air, and that comes from oceans, lakes, and stuff like that. Even plants, what's called transpiration, which is where plants are actually taking in water out of the ground. They utilize it, part of its photosynthesis process, and then releases water into the air. It doesn't seem like there's that much, but if you've ever gone through the forest on a hot day, you'll notice it gets very, very humid and muggy in the forest. That's from the plants doing transpiration. The other thing, in order to form a cloud, the air must be warmer than the surrounding air so that it rises. So you must have rising air. So humid air must rise from the surface of the earth to begin to cool, and we get to cool to get well, in order to cool, we have to hit 100% relative humidity. So we take that moisture that's in the air, we start to rise it. As it starts to rise, it cools, it hits 100% relative humidity, and that's when either one or two things form, depending on the temperature of the air aloft up in the cloud. Either you're going to form little droplets of water, and when you're looking at a cloud, really what you're looking at is little droplets of water. It's basically like fog. It is fog. Fog is clouds, clouds, and fog. Kind of wrap your mind around that. If you've ever driven up into the mountains and you've hit the clouds, you notice that you go into a fog. And all fog is just little droplets of liquid water that are just suspended in the air. You look closely in a fog, you'll see little droplets of water floating around. Or if it's cold enough, it's not little droplets of water, it's little ice crystals that form up there. And that's kind of basically what you need in order to form a cloud. There's something else that you need to form a cloud too, and I'm going to discuss this at the end of the video, because I know this video is going to be a little bit long, and I want to give you the option of sticking around only if you want to watch this part. And it involves this thing, which I know some of you guys are going to think this is not what you think it is. But I'm going to make, actually, it's almost like a magic trick. I'm going to make a cloud inside of this contraption. But I'm going to do that at the end of the video. Alright, so once you make a cloud, what comes out of the cloud? Well, what happens is that those little water droplets or little ice crystals, they start to form inside of the cloud. They get larger and larger and larger until pretty much the pushing up of air, they can't handle it anymore. Gravity takes over, they become too big, too massive, and they fall down. What they fall down as is a few different things. If it could fall down as a straight up rain. If there is a situation where the air is moving up so fast that the little droplets of water can't fall to the ground because air is moving up. It's like almost think of wind blowing up into the cloud. It might push it up higher, causing the little droplets of water to freeze, coalesce, and get larger and larger and larger until it falls down. Finally, gravity takes over. It's able to defy the wind, and it falls down as hail. You miss most of the situation, particularly here in the Pacific Northwest, is like this right here, where most of the clouds produce snow first. So you have ice crystals that grow and grow and grow until they can't be suspended anymore, and then they fall to the earth. But we don't get snow because the air down here is warmer, so it'll come down as rain. Or there's some situations where, in this case, you might have very, very cold temperatures at the very surface of the earth. So you have cold air up in the cloud, and then warm air, and then very, very cold right at the surface, and that might come down as sleet or possibly even freezing rain. And it's like the worst possible scenarios. Or the air stays particularly cold. You might get something like called graupel, which looks like snow, but it kind of makes a sound when it hits the ground. Snow shouldn't make a sound when it hits the ground. And it's not quite hail, so they just look like little styrofoam chunks falling from the sky. We call that grapple. Or you could just have snow if the temperature is kind of cold from the cloud to the ground. Alright, and I would suggest going back and looking at this video and seeing what's going on with this. This would be very, very useful in understanding why you get the weather that you're getting. Okay, how to make clouds. Once again, there are different types of clouds that we could be talking about. One is called a convection type cloud. What you're looking at in the background picture there is what's called a cumulus cloud. A cumulus cloud is basically a convection cloud where you just have a land surface. The land surface gets hot. There's a body of water somewhere, not in that picture, but somewhere near that, maybe a large lake or an ocean. And remember that water can travel in water vapor across the land. I mean, you can have it's coming off the coast of Texas, making it all the way into Arizona before it finally goes up. So the air gets lifted up, and you can really see as that air goes up. Right here, this point right here, that's where it reaches 100% relative humidity. The air has cooled off to where it can't handle that moisture anymore. So that is the point right there where we're at 100% relative humidity. Anything past that is going to be where that water is being condensated, and it's just being pushed up by that low pressure, keeps being pushed up into that cloud. So really what you were looking at with this great big cloud right here, called a cumulus cloud, is a bunch of little water droplets that are growing and growing and growing. And that cloud will get bigger and bigger and bigger until it can't hold that moisture anymore, and that moisture starts to fall out as rain. A cumulus clouds are usually referred to as the big puffy clouds. When you look up there and say, ooh, that looks like a wiener dog. Those are typically cumulus clouds. When those clouds do actually have water coming out of it, we refer to that as cumulonimbus. Nimbo is the Latin word for rain. The next type, and this is something that's very familiar here in the Pacific Northwest, is what's called orographic uplifting. Orographic lifting is, you'll see this on Mount Rainier. This is actually a picture of Mount Rainier right here. And you've probably seen, I always say it's got its mariner's hat on. It's got like a little cloud. Yes, I'm using my head as a mountain. It's got a little cloud over the top of it like it's wearing a cap. And sometimes it's got clouds stacked on top of clouds and stacked on top of clouds. So what's going on there? Well, we got something that's called orographic uplifting. And what happens is from the Pacific Ocean, we get cool, moist air, and it's being pushed up on land. So instead of being convected up by heat, it's being pushed onto land. But the land, the Cascade Mountains, go up. And so now what happens is you're starting to push that air up. It starts to compress and cool, so it hits that relative humidity really quick, and it creates clouds. And this is one of the reasons why we're so wet here in the Pacific Northwest. When you drive out towards Mount Rainier, you see a lot of trees. When you drive towards the pass, you see a lot of trees. Those trees like the rain. We're technically a rainforest here in the Pacific Northwest. And that's because it's being pushed up to form a cloud. Now what happens is once that air reaches the top of the mountain, it starts to go back down the other side. Well, air that's going down is heating up. And if it's heating up, we're going to drop below 100% relative humidity really fast, which means it's going to dry out. So if you've ever driven to eastern Washington, you've gone over Snoqualmie Pass, you'll see trees as you go up the pass. And then as you go down the pass, it's desert. This is called a rain shadow, and it's typical of mountains to not get much rain on this side. Even we think about this side of the mountains as being very, very wet, and it rains all the time. But if you go to the other side of the Puget Sound, I think the name of the town is Sequim, they get very little rain there because the Olympic Mountains are doing the orographic uplifting. All the rainforest is on the west side of the Olympic Mountains. On the east side of the Olympic Mountains, it's actually really dry. Another way to move air up is called a front. Now, if you guys remember, we talked about, I think about 2 videos ago, we talked about general direction of air movement on the Earth. At the equator, it moves up because it's warm air. At the poles, the air moves down and moves over the surface and is pulled to the right by what's called the Coriolis effect. That air that goes up from the equator eventually has to come back down, and it creates a high pressure system in this area where air is sinking down, and it moves over the surface of the Earth and is pulled to the right because of the Coriolis effect. Well, if you can imagine, you have air that's coming from the north, this polar air, and air that's coming from the south. Where they run into each other is called a polar front. And they don't stay. It's not like a straight line. It doesn't follow a latitude line. It's very, very chaotic, I guess I could say, as to where that line goes. It meanders back and forth like a river. And in some situations, if you get a low pressure system, air that's moving up on that line, then what's going to happen is you get that cold Arctic air kind of coming down like this, and warm tropical air coming up like this. So and it's all going to go kind of around in a circle, and that cold air is going to run into that warm air, and that warm air is going to run into that cold air. When that happens, when you have this line of warm air, in front of that line is going to be what's called a warm front. In front of the cold air, we're going to call that a cold front. So you're going to have like a day where you're like right here, and this whole low is moving towards the east. So if you're like right here, it's warm day, warm day, warm day, and all of a sudden it'll be cold day. That's why we call that a cold front. Now, this affects how clouds move. One of the things you have to know and understand is that air does not mix. Cold air and warm air, the 2 different densities, they don't like to mix with each other. So they will actually create really a barrier, a boundary between the 2. And because warm air is warm and cold air is cold, the warm air will be pushed up over the cold air, or the cold air will be pushed under the warm air. And you can really see this in this picture of the United States. Yellows and reds are showing warm air, and blues and greens are showing cool air. So here's your warm front, it's in front of the warm air. Over here you have your cold front, which is in front of the cold air. We can see that it's got polar air coming in from the south, tropical air coming from the polar air coming from the north, and tropical air coming from the south. Alright, so let's talk about warm fronts and what does that have to do with clouds first. So here we have warm air, and there is your warm front, and it's usually represented with a red line because it's warm, with these little bumps on it. All right, so if you see a weather map with a line with little red bumps on it, that's called a warm front. Well, because warm air is going to run into the cold air, it's in front of the warm air, and it can't mix with the cold air, so it's going to be pushed up and over. Once again, just like going over a mountain, it's going to go up and over the cool air. It's going to form clouds. This time the clouds are going to form, instead of like big puffy clouds, it's going to form in layers. They're going to layer on top of each other. Another word for layer is strato. We use the word strato a lot to call layers. So if it's rain clouds, we call those nimbostratus clouds. And as we go higher, you start losing, a little bit further, and you start losing moisture. It's all given up in that rain and the nimbostratus clouds. So you'll get like stratus clouds. Alto. Alto is Spanish word for tall. That's actually the word Spanish word for tall comes from the Latin word alto. Altostratus just means the higher level layered clouds. Cirrostratus, and then cirrus. And underneath it would be kind of no clouds because it's got that cooler air that's moving down. So another word for layered is stratus. One of the great things about a warm front is that you don't need to listen to the weather to find out what the forecast is going to be, because if you're right here and you're looking up and you're seeing stratus clouds, and then a little while later you're seeing cirrostratus clouds. If you see cirrus clouds, cirrostratus clouds, altostratus clouds, if you see that progression marching towards you, you know that within the next 24 hours or less, you're probably going to be looking at rain. as that warm front comes through. This is really, really typical of the Pacific Northwest. You'll go outside one day on a nice sunny day. It might be clear out, but a little while later you start seeing these little, it looks like horsetails. These are the cirrus clouds. I'm not joking, I'm serious. A little later on, you might see what's called cirrostratus clouds. So those cirrus clouds start to layer up. Then you start seeing these alto. I like to think of these clouds to figure out what an altostratus cloud is. It's like you see a whole bunch of clouds kind of layered up in the sky, but they're still high enough to where you see airplanes flying underneath them instead of on top of them. And then, of course, you have what we're used to here in the Pacific Northwest, the nimbostratus clouds, those low-lying stratus clouds, where you're pushing a lot of moisture and it's going to create rain. With a cold front, it's really different because cold air moves like, if you can imagine a little blob of water on a table and you were blowing on that table, the blob of water would kind of be steep on one side and shallow on the other as it moves. And this is what happens with a cold front. So here we have cold air, and you can see it's steep right here, and it's running into warm air, and it's forcing that warm air straight up. In this case, all of the moisture is being pushed up into the cloud vertically, almost like it was a convection type cell. And because it's like that, it's going to produce big old cumulus clouds, huge cumulus clouds. And what typically happens, since this is all of a sudden, if this cold front is moving towards you, there's really not going to be much warning, first of all, that this cold front is moving towards you. You'll just notice a change in direction of air, and you'll notice that the air starts picking up, blowing faster and faster and faster, and then all of a sudden, boom, you're in a storm. And this is actually quite a dangerous thing because these storms tend to be a lot more intense than with a warm front. You get heavy rains, which means flash floods. You probably get thunder and lightning with it. It's likely that you'll get high winds with it. And if you live in some places in the United States, cold fronts are often associated with tornadoes. So this is the nasty type of weather. Now, not all cold fronts are that bad, but typically speaking, cold fronts mean heavy weather, heavy rain, high winds, and possibly even hail, and possibly even some thunder and lightning as that air moves in. And it's usually quite sudden. So if you've ever heard of people who live back in the Midwest, in Iowa and Nebraska and Kansas, where you have a storm that comes on suddenly, and then all of a sudden you're in a tornado warning, that probably was a cold front moving in. Here you can actually see, you can literally see the cold front. This would be, over here would be the warmer air. Behind these clouds would be the cooler air. And what's happening is that warm air is being pushed up and over that warm air. I mean, you can literally see it as it's coming. I always like to think of it as back in the day, the Native Americans used to have a mythical creature called the phoenix, which was a mythical bird that brought lightning and chaos, and it would rise from the fire and stuff like that. I think that story kind of comes from typically what happens if you see birds riding a thermal. Basically, birds that are not flapping their wings, but they're spiraling up. That's because they're riding what's called a thermal. Thermal means that air is rising up, and all a bird is doing is rising it up. So they would see all those birds kind of gliding in front of these great big old scary thunderstorms that were coming. There would be thunder and lightning behind the birds, and the birds would be leading the way. And that kind of comes down to what the whole myth of the firebird or the phoenix. A couple other types of fronts. I don't want to go too much into this. One called a stationary front, and that's when the air system stops moving. So instead of getting a cold front or warm front, because it's not moving, there's no front. But there's typically, you got a collision of cold and warm air, and that's a mixture. So I didn't even mention anything in this PowerPoint about that. This is another one that's kind of interesting. Here you have a cold front, and you can see right now the cold front is starting to overtake the warm front. So that would be cold air, and it's now pushed the warm air all the way up, and it's got cold air, but you still have clouds that are kind of trapped on top of those two cold air masses. And Typically, it means rain, depending on where you're at. But if it's in the wintertime, this is the thing I like when I'm, trying to figure out in school. Are we going to have school next week? What's the situation? Are we, in December or January or February with the whole snow thing? Well, when I look for snow things, I actually look for something that looks very much like this. A cold front, probably not going to produce that much snow. A warm front's definitely not going to produce snow. However, if you're up here in this occluded front, that means it's going to precipitate out of those clouds. It's going to rain or snow. And if the air is cold enough from this cold air, then you might actually get some snow. This is typically where we get snow, particularly here in the Pacific Northwest. So you want to look to see if we have an occluded front, if we're in the top of this. By the way, the middle of the low pressure system is usually about right here. So that's occluded fronts are actually kind of important, and they really don't talk about that much when they talk about it on the weather, because I don't think a lot of people know what occluded fronts are. All right, the last thing I talk about is what's called continental air masses. This is really important. I wish we had more time to get into this, but this is going through and looking at what is the air like that you're getting in any particular area in the United States. And remember, this shifts as the Earth is shifting on its axis as we go around the sun. Warm air tends to move up during the summer, so these red blobs down here move up during the summer, and these cold blobs move down during the winter. But what you're looking at here is a description of generally the air in that area. So think of these as blobs of air. This would be called maritime polar. Maritime is just another word, like mariner is a person who's on a boat. Maritime is just another way of saying ocean or sea or large lakes, a large water mass. So that means that there's a lot of potential for humidity inside of that air to make, clouds and stuff like that. Continental, on the other hand, means that air is coming over a land mass, which means there's not going to be a lot of moisture. It's going to be dry air. Polar means that it's coming from the poles. So we're generally getting these colder air masses moving down. So we either have maritime polar, which means cold and moist. Continental polar, cold and dry. Maritime tropical. Now, tropical means warm air, so this would be warm, moist air. And a lot of times, particularly during the summer, we're getting maritime tropical air coming into Washington. During the wintertime, we get more maritime polar coming into Washington. Continental tropical, that's the desert areas. And maritime tropical, if you live in the southeast, you'll know you'll know it, Florida, Louisiana, Alabama, Texas, to some degree, the coastal parts of Texas, Tennessee, South Carolina, North Carolina, even Kentucky, even going all the way as far as like Minnesota. When we get into summertime, that maritime tropical air kind of pushes into the United States, and it gets very hot and it gets very humid. And that's because of that tropical air that's moving in. So this is kind of the whole situation of what's going on, and how these air masses, they don't stay still. They move in. They're like big blobs of air, and they're just kind of moving across the globe. And how they move across the globe will determine what kind of weather you're going to have. For example, if you have this continental polar air moving this way and this maritime tropical air moving this way, then what you're going to get right through here would be a cold front. Notice that cold front is right here in this region of the United States. We call that Tornado Alley. Why? Because of the conversion of those different air masses all in one area. Becomes a very, very dangerous area, particularly with the cold fronts, where it produces what's called wind shear. And wind shear is just when air is moving side by side. Well, imagine if you're a little bit of air and you're stuck right in the middle of those two airs moving side by side, you're going to start spinning. And that's where we get things like called tornadoes. And this is actually quite unique to the United States. There's not very many places in the world that even have seen tornadoes. When the settlers first moved to the United States from Europe, or Africa for that matter, they never had seen anything like a tornado. They had no idea that these things, these very destructive, very scary things, even existed. So if you can imagine, you come in and settle into the new world, and all of a sudden everything that you have, everything that you know, is wiped out by this swirling windstorm. It was crazy and frightening to them. Even to this day, people still get affected by them. Now here in the Pacific Northwest or the West Coast, we don't get these too often, but we do get cold fronts that come through, which means we always have the potential of having tornadoes in the Pacific Northwest. Not bad ones, because our weather is a little bit milder. It's not as extreme as it is in, say, Kansas and Oklahoma. But we do get, on average, about 2 or 3 tornadoes per year in the state of Washington. Fortunately, most of the time, they're, like I said, mild tornadoes, and they're usually in the middle of the forest, not in a city, so you don't hear about them. But they do happen. Okay, that's it. That is it for our weather unit. This is where I'm going to end for the year, because basically we just kind of ran out of time. I would love to talk more about things like why we have lightning, why we have rainbows, hurricanes, so forth and so on. But I do remember I was going to show you one more thing before I left. Oops. And my thing went away. Hold on. What happened here? I'm going to have to zoom me in. There we go. And this crazy contraption, no, Mr. Lee is not going to smoke a bong on video. I'm going to lose my job that way. Plus, I would never, ever, ever do that. This is not a bong. This is what's called a cloud simulation chamber. And basically what it is a glass tube, and I've created a vacuum inside of it. So there's a little air in there, but it's clamped off at the top, so air can't get out. And what happens if I can squeeze this blue ball right here, and when I squeeze that blue ball, it's going to increase the pressure inside the glass tube. Now notice I have water inside the glass tube. Swish the water around, and as I swish the water around, what I'm doing is I'm partially evaporating the water into the air of the tube. And the relative humidity inside of the tube right now, if we were inside that tube right now, I'd be like, oh my God, it's so humid in here. It's right near 100% relative humidity. It's that close to dew point. And if I squeeze the ball, what happens is I compress the air. When I compress the air inside of the ball, then the relative humidity, the temperature inside of the air compresses. And when you compress air, remember we've talked about this several times in this class, when you compress air, you heat it up. And when you heat it up, the relative humidity drops. So it dropped to about maybe 80-something% relative humidity. But I'm going to press it and I'm going to swirl it around again. And now as I swirl it around, I'm putting the water vapor back into the air. So now at this newer, warmer temperature, it's going to be a higher relative humidity. So we're back up to about 90. Now I'm going to let go of the ball, and what's going to happen, I'm going to decompress the air, which means that the air becomes less, the air will increase your relative humidity, and it will go over 100% relative humidity, which means when I let go, I should form a cloud, right? So I'm going to let go, and nothing happened. But I know inside of this chamber, I went over 100% relative humidity. I should have a cloud. The cloud did not form. Why not? Well, it turns out there's one more thing that needs to happen. You have to have moisture. You have to have the relative humidity drop. You have to have the relative humidity go over 100% so we reach dew point, which it did. But the water vapor actually has to have something to condensate onto. It needs a little speck of something, a little piece of dust or something like that, that the water can actually grab onto and become a water droplet. It doesn't need that much, like pollen in the air, dust in the air, smoke in the air. All of that works, and you can't really form a cloud until that happens. So what I'm going to do is, and it's going to be kind of hard for me to show you guys exactly what I'm doing here, so I'm going to show you, I have got here some matches, and I am going to create a fire. And you guys are really wondering, Mr. Lee, now you got matches. What is that contraption called, really? cloud chamber. Okay, so that produces a lot of smoke. And I'm going to take a clamp off of this tube, and I'm going to blow this out, and I'm going to suck the smoke into the tube. All right, I've sucked it into the tube. Put the matches off so it doesn't set my office on fire. And I'm going to clamp it off again. All right, now you could probably faintly see in there, it's not really that great. Let's move my head out of the way, find a dark area. It's not that great. You can probably see a little bit of smoke in there, but not much. But I'm going to do the same thing. Now what I'm going to do is I'm going to squeeze the ball, increase the relative humidity, and swirl it around. I'm sorry, just decrease the relative humidity. Swirl the ball around, and now we're at about 99% relative humidity, right about dew point. But now there's smoke in there for water to kind of collect onto. So now when I release this, did you see it? Do it again. Find something dark, get my head out of the way. Okay, you can see the cloud disappear. We went below dew point. And there you go. So I'm forming a little cloud. Camera's not doing a great job of this. And we formed a cloud. And that's kind of how clouds are formed. By decreasing the temperature and finding something for that water to cling on to. All right, that's it. That's all I got. That's our last video for the year. So I hope you guys have got a chance to enjoy these videos. If you have any questions, as usual, feel free to email me, contact me, remind.com, so forth and so on. Do miss you guys. I wish this would have been in the classroom, and hopefully someday soon we won't have to watch videos. We can actually do these things in the classroom, and you guys can ask questions and so forth and so on. Love you guys. Miss you guys. And you take care and stay well, and hopefully we'll see you guys next year in a different science class. Take care.